I'm Jake O'Neill, creator of Animographs. And over the last few months, I researched, scripted, 3D modeled, animated, and scored this project. This is how an early 20th century steamship works. I've chosen to feature a combined cargo and passenger ship. Our obsession with this era centers around the most famous, most extravagant vessels. So I wanted to instead show a day-in, day-out workhorse kind of ship. That said, there were literally hundreds of thousands of big steamships operating at this time. Standardization across the industry means what you see here is pretty much repeated on the more famous ocean liners, but on a way bigger scale. Our ship is designed to carry passengers and cargo across the Atlantic, a journey that takes 10 to 12 days at an average speed of 14 knots, which is about 16 miles per hour. She's 500 feet long and 70 feet at her widest. Here's our ship next to the Titanic for a size comparison. As you can see, she's no slouch, but our workhorse vessel has just one funnel stuck straight out the top, instead of 4 regal chimneys at a jaunty backward slant. Our ship is slower, but very dependable. Titanic was rated for around 21 knots, or 24 miles per hour. We can carry 500 passengers. With about 450,000 cubic feet of cargo space. Though they couldn't actually be lowered into the ship, that's enough theoretical area to transport about 170 modern 40-foot shipping containers. Of course, a modern ship with a matching size would be considered a small regional shipping vessel, but with the ability to carry 3 to 4 times that container count and weight. The skeleton of the ship is built from riveted steel plates, formed into beams, frames, and so on. Metal welding was an experimental technology at this time, so even the main outer steel shell or hull of the ship is made from alternating riveted rows of steel plating called strakes. These riveted plates cover every contour of our hull, even complex areas like the propeller shaft support at the back or stern of the ship. The basic layout of our ship puts first-class cabins and social areas near the center, where the ride is smoothest. Expansive cargo areas spanning multiple decks sandwich first-class areas, basically taking the place of what would be second-class accommodations. At the very back, the roughest and least adorned passenger areas, the steerage, or third-class accommodations. Motive power is produced deep in the belly of our boat. With 6 coal-burning boilers, 3 to a row, facing each other. Exhaust is channeled up and out of the main funnel. Behind the boiler room, there's the engine room, with 2 huge steam-powered engines that put out around 4,000 horsepower each. direct connected shafts run all the way back to 2 counter-rotating propellers. We're going to look at all of these areas and systems in great detail. Let's head to the top of the ship and start our exploration at the Wheelhouse. The Wheelhouse is where immediate, moment-to-moment navigation takes place. At the center, we see the ship's main steering wheel. Ships grew to such great sizes that simple ropes or cables directly connecting a wheel to the rudder would experience forces far too great for a lone human to handle. Our wheel is connected to a steering motor at the back, which drives the rudder. We'll dissect this compartment once we make our way back there. Just above the wheel, there's a tube with a wide opening. This is a voice tube which officers speak into for communication and vocal commands. The tubes lead into the boiler room, engine room, and more. In front of the wheel, there's an enclosed compass on a pedestal, called the binnacle. The cylinders at each side are for oil or electric lamps. Below the lamps, there are spheres at each side for calibrating the compass. As ships began to be made of metal instead of wood, the great mass of metal interacts with the Earth's magnetic field in various ways, such that a magnetic compass on board can no longer accurately point to magnetic north. The soft iron spheres tune magnetic forces around the compass so it functions properly again. There's also a hanging vertical iron bar in the pedestal. And sets of small permanent magnets on movable trays. We're correcting for things like permanent magnetism induced in the ship's hull during the construction process, the change in magnetism as the ship moves toward or away from the equator, and errors caused when the ship is rolling or leaning on heavy seas. There are 2 engine order telegraphs because our ship has 2 engines that can receive different commands. The outer handle is moved by an officer here at the Wheelhouse. The smaller pointer moves when an engineer at the engine confirms the command on another telegraph like this one. The central telegraph has docking orders instead of engine instructions, with a receiving unit at the back of the ship for use during the careful process of docking. A deck-mounted lever here controls the ship's main steam whistle. Which is attached to the front of the funnel. There's an exposed platform at the highest point on our ship, over the Wheelhouse. This is the flying bridge. Some controls are duplicated here, like the steering wheel and engine order telegraphs. There's also a powerful electric searchlight. And at the end of the platform at each side, a device called a Propellers. The Propellers has a compass card and a sighting vane, but it's not magnetic. An officer takes a reading from the ship's main compass below to calibrate the card, while using the sighting vane to spot a landmark, star, or other known object, and thereby find or confirm the ship's coordinates on a map. Using two Pelorises at distinct viewpoints makes for more accurate readings, while avoiding sightline obstructions down the center of the ship, front and back. Moving down below again, we head into the Charthouse, which sits just behind the Wheelhouse. Here, the ship's navigator plots and maintains the ship's course on detailed nautical maps called charts, while also keeping detailed logs. There's a personal storage and a bed here also. An open stairwell leads to the deck below. The Wheelhouse and Charthouse together make up the navigating bridge. As we descend the staircase, we land at the boat deck. Here at the front, there's the captain's personal quarters and bath at one side. A lobby and storage room in the center. And the chief officer's quarters at the other side, with a spare room. Note that the exterior-facing doors here are quite high off the outside deck surface. Parts of the ship exposed to the ocean like this need ample protection from flooding. Heading outside, we see why it's called the boat deck. There are 8 steel lifeboats at the sides. With 2 workboats at the front. Whereas the lifeboats are for emergencies only, workboats can perform many essential duties for ship operation, such as ferrying personnel back and forth if the ship must anchor away from a dock. Or circling round the ship to record draft numbers painted on the hull and thereby track how far down into the water our ship sits, front to back, for load balancing and weight regulations. Lowering any of these boats is a serious endeavor. Superior devices were in use even at this time, but our workhorse ship uses an older, simpler, very common lifeboat lowering setup with curved arms called rotating davits. Sailors wrangle the boat out over the edge by pushing the side and tending lines at davit ends. The back end goes out first, allowing the lifeboat to pass between uprights. Then the front is swung overboard. Another set of lines with pulleys and a friction device called a bollard allow sailors to lower the lifeboat to the ocean below. Now, let's load this boat with passengers. I'm showing 36 passengers here, where the boat would have a rated capacity of 30 to 40 people. In heavy seas, the ship might have a lean or list to one side. Now, rotating the davits and controlling all loose ends becomes quite the harrowing scenario. The drop from boat deck to the ocean is about 40 feet, the height of a 4-story building. Additional lines or tools might be needed to keep the boat from smashing into the ship's side. And it must be released immediately on touching down, or risk being yanked back up into the air as the big ship rolls to and fro. It's easy to see why regulations regarding lifeboats were updated in later eras. As we head indoors here at the boat deck, we see comparatively spacious rooms for high-ranking officers and personnel, with associated bathrooms. There's a radio room here as well, where the wireless officer continuously monitors and operates wireless telegraph equipment. The radio antenna is suspended high above, between cargo boom masts, stretching over 2/3 the length of the ship. Behind the radio room, there's the officer's dining saloon. Which is serviced from a nearby pantry. With a dumbwaiter that descends through multiple decks to the ship's main pantry and kitchen or galley, far below. Moving aft, we start to see some of the fine first-class accommodations. Even our working-class ship would likely have luxurious decoration in these areas. There's a first-class lobby here between other dedicated spaces. And a writing room with desks, paper, and so on for writing letters and preparing mail that would be collected at the next port. At the back, there's the tea room, which functions as a less formal social area or cafe-type atmosphere. A curved window wall looks over a balcony, with views of the sea and decks below. Let's head down. This is the bridge deck. We're still one deck above the ship's main deck. There's a spacious veranda here at the back. That leads into a dedicated smoking room with more fine decorations and a large central fireplace. Moving forward, there's a lobby for the main staircase. With doors to the first-class promenade at the ship's sides, which serves as a more protected area to take in the outdoors. This is where many passengers would enter the ship. At the front, there's the main social hall. Where the writing room and smoking room were considered gender-specific spaces for the time period, the social hall is the great gathering space for collective events, outside of the main dining hall, which is situated on a lower deck. Moving outside, we pass a portable swimming tank for passengers. Before entering the separate forward structure again. There are bedrooms here for high-ranking officials or special guests. With sitting or meeting rooms at each side. And small storage closets for travel trunks, apart from the ship's main passenger trunk storage below. A staircase here leads us down to Deck A, which is the ship's main deck at the exterior surface. As we head outside toward the bow, we can see the extensive array of cargo handling gear. Our ship has 9 cargo hatches for access through decks to the very bottom of the interior below. Not only for shipping cargo, but also for stocking the ship's own supplies. For example, there's a hatch tucked into the tight space between the navigating bridge and social halls with a removable walkway for access. A similar hatch sits at the back, on the smokeroom veranda. The green tarps ensure a well-protected, watertight opening. Sets of planks are placed below that. And can be adjusted at each deck to form a temporary floor area between decks depending on cargo requirements. This is a time before shipping containers became standard, and cargo handling, or stevedoring as it's called, is a much more time-consuming, hands-on, and dangerous process. Items are shipped in all shapes and sizes, but you would generally see crates, bales, sacks, wooden barrels, and so on. Cargo is packed in fairly tight so that it can't easily shift. This much weight, if loose, could easily throw the entire ship out of balance in heavy seas. Some loads might require additional measures to secure things in place, with wood beams called dunnage between layers. Shoring at the sides, and tomming down at the top. The booms at the main deck require skilled, careful control. Goods are dangled over cargo holds far below, in rigged-up rope slings. Let's look at the boom and steam winch setup. The winch is a complex mechanical unit. Much of the equipment we'll see going forward will have noticeable steam motors attached to it, like those you see here. Steam-driven pistons power the device's gears and wheels. The main lifting line is a galvanized steel cable wrapped around the drum. The drum is controlled by a lever for forward, reverse, or braking. There's an additional cylinder at the end that always rotates while the winch is in operation. The drum end man can wind a rope either direction and use the friction of the rope itself around the rotating cylinder for any number of boom-related tasks. With 4 of these winches at this mast alone, you can start to get an idea of the steam plumbing nervous system that snakes through nearly every part of our ship. This will become even clearer as we go along, since most things run on steam, even though there are some electric components on board. Since cargo could be anything and everything, there are almost unlimited methods for rigging, lifting, and stowing items in the hold. I've shown a clever method here where two booms are positioned and hooked to a load at once, so that by alternating winches, the load travels the entire loading path without having to reposition booms. Continuing toward the bow, there's the sounding machine at one side. Our simple model has a crank, but steam or electrically powered devices were also in use at this time. This is how water depth readings are taken. There's a lead weight at the end of a long cable. The dial goes up to a max 290 fathoms, or 1,740 feet deep. Grease or rendered animal fat is packed into the lead weight, which is then lowered overboard. The machine is stopped as soon as the line shows slack, indicating it has reached bottom. When the weight is cranked or hauled back up, samples of the seabed can be compared with onboard charts to indicate ship location, apart from water depth alone. More advanced systems had components in the metal weight that react to water pressure for better depth readings. This dial simply shows how much line has left the machine, and can't tell, for example, if the line is hanging straight down from the deck level, which would affect accuracy. Near the sounding machine and occupying much of the bow deck area, there's the anchor and windlass. Which is a steam-powered cranking device to handle the massive anchor chain. The chain passes through thick steel tubes called hawse pipes. Into which the anchors are secured and protected while underway. There's a heavy iron chain stopper on deck. An opening below the windlass leads to chain lockers beneath. Heading aft again, let's look over the interior spaces here on Deck A. We're still in first-class territory. At the front, there are rooms and offices for the chief steward, or head of hospitality on deck, like a hotel manager. And the purser's office for handling financial and other record-keeping duties. To the sides of Deck A, there are spacious staterooms with single beds, where most other cabins will have bunk beds to conserve limited space. Steam radiators provide heat. A fancy stairwell leads to decks below. A stained glass dome allows additional light into dining areas beneath. Toward the back of Deck A, there are rooms designated as hospital quarters at each side, and shared restrooms. Restrooms, by the way, are plumbed in banks to outlets called scuppers, just above the deep load water line. They simply empty to the ocean, and while discouraged, flushing toilets was not strictly prohibited while docked. As we continue aft across the open deck and past multiple cargo hatches, we finally see the third-class entrance and deck access. Again, our ship has no designated second-class areas, likely because the design is a common one for its time, and those spaces are taken up by cargo holds in our case. There are stairwells here going down. There's a storage room and kitchen or galley to serve the third-class passengers. Let's descend into the third-class area, otherwise known as steerage, for its proximity to noisy steering and rudder components. This is Deck B, still one deck above the water. You can already see the gist of third-class accommodations. Metal bunk beds called pipe berths crowd the communal deck space. With an open dining or mess area at the center. The tables are set directly over cargo hatch boards. And the hatch is open and not trunked, or isolated by walls, like we've seen with first-class areas. Communal bathrooms at the front and back of the space have small tubs for washing. But not full bathtubs or showers as with finer areas of the ship. And the water flowing from all taps is cold salt water. Laws had already been made to improve unsanitary steerage conditions of the time. A fortified partition called a bulkhead separates the steerage area from the first-class rooms as we move forward. There's a laundry closet here for storing used linens. Washing capabilities weren't yet common on ships of the time, so laundry is stored and washed in port. Most of these first-class rooms are designated as three-person cabins. With a bunk bed to one side, and a sofa at the other that converts into a bed. There's a fold-out washstand between the sofa and beds, with a basin for light washing. Which may be connected to the ship's main plumbing, or simply drain into a bucket below to be emptied by stewards. As we continue through the row of first-class rooms, we see more shared bathing facilities. These would all likely operate with salt water, though it was filtered and could be heated as well. Salt water was generally regarded as having beneficial medicinal properties. Nearing the center of the ship, we see rooms for onboard stewards, or hotel staff, as it were, with private bathrooms and showers. To the left or port side of the ship, we arrive at the main first-class galley and pantry, where all meals are prepared and managed. At the center, there's a huge coal-fired galley stove. With multiple smaller coal boxes for individual fires around the unit. There's a sturdy rail at the sides for cooks to grab onto as the ship moves. Tilting 40-gallon stockpots sit nearby. A bun prover cabinet uses steam for a sealed, temperature-controlled environment to raise bread dough. There's a stairwell which connects to additional food storage and preparation spaces below. A meat slicer and meat prep table runs down the opposite side. There are electrically powered units here, a potato peeler, cake mixer, and dough mixer. These are just a few common items in a galley of this size. To feed 500 passengers every meal daily, the kitchen would be literally full of pots, pans, a team of 20 to 30 personnel including cooks, bakers, butchers, and pantrymen. The neighboring room heading forward is the first-class pantry. This is where food is plated and otherwise made ready for taking out to dining passengers. There's a metal sink and an electric dishwasher. A hot table and bain-marie or hot water bath keep food and food trays warm for extended periods. There's a formidable array of plates and associated utensils at the pantry counter. With hundreds of coffee cups on hooks overhead, though you'd likely see fine glass drinkware as well. The curved bar at the front is where stewards pick up meals and take them into the dining area. This is the first-class dining hall. You'll notice the stained glass dome overhead, which we saw protruding through the deck above. There are ornate chandeliers with fancy tables and upholstered chairs. Of course, these spaces are even more ornate and detailed than my model. The dining hall takes up the entire space between ship sides. Leaving the dining hall, we see the main staircase at this level. There are more first-class rooms at the sides with bathrooms. And staircases going up. Cargo space continues here. In front of that, there's the onboard carpentry and machine shop, with a few electrical power tools. The anchor chain chambers run through this space as well. And more storage space in the bow. Let's head aft again and find our stairs down to Deck C, tucked under the main staircase. As Deck C comes into view, you'll notice the trimmings are quite sparse in these parts. That's because this deck holds quarters for the ship's crew and mechanical systems. Starting aft of our continued cargo space, there are separate mess or dining halls for officers of varying ranks. Cabins at the front here are reserved for officers, onboard carpenters, and stewards. Heading farther aft, at the right or starboard side, there are quarters for more stewards. The chief cook and chief baker, and supporting cooks, butchers, and lower-class kitchen labor like scullions or plate washers, and pantrymen. The kitchen staff have their own mess hall here as well. At the other side of Deck C, we have quarters for personnel who run the boiler, engine, and associated mechanical systems. There are firemen's quarters, oilers, wipers, water tenders, and more. We'll see a few of these roles as we descend deeper into the ship. Behind that, we see kitchen support spaces that are accessed from the galley staircase we saw on Deck B. At the foot of the stairs, there's the butcher shop, which would be full of meat cuts. Down the hall, the bakery. With a large baking oven along one side. Another bun proving cabinet, and work tables. Flour storage sits behind that. And a main laundry storage room. The remaining rooms with shelving units you see in this area are actually refrigerated compartments, with separate rooms for vegetables, poultry, fish, butter and eggs, meat, and so on. As you can see, the refrigeration capabilities on board are extensive. There's even more to this system on decks below. Cargo spaces fill the after capacity here. Followed by lower-level steerage class quarters, which are mostly similar to those we saw on Deck B. There's a protected access here and a staircase. Let's descend down to Deck D. Here we land in the steering compartment. This heavy machinery is directly attached to the rudder below. As I was saying at the steering wheel, ships had become so big that mechanical assistance is necessary to handle the forces acting upon the rudder. This is a steam-powered steering engine. You can see the steam motors at each side that work quickly to turn the main gear set and quadrant as steering inputs arrive from the wheel. A quadrant, or quarter of a gear, is used for maximum leverage in the limited space here at the stern. It features separate moving parts with suspension springs to shield it from ocean forces as they beat upon the massive rudder. The way steering inputs arrive is quite unique compared to other systems on board. This is a telemotor setup. The small piston rig here is an early hydraulic device, but it doesn't use oil like modern hydraulics. Instead, the lines which connect this unit to the main steering wheel are filled with water and glycerin to prevent freezing. Steering wheel inputs send pressure changes through the lines to the piston here, and then to steam motors with mechanisms to echo these commands precisely. cargo space fills the areas heading forward. And we see additional refrigeration compartments ahead of that. The empty space in the center is in fact a tightly packed area spanning both of the lowest decks for the boiler and engine rooms, which we'll see next. Forward rooms here at Deck D include a dedicated mailroom, and protected safe deposit room. Also nearby, the main trunks and baggage storage area. The lowest and final deck of our ship is the hold. It's all business down here, packed wall to wall with cargo and vital mechanical systems. As you can see, the boiler facilities take up an enormous amount of space. The walled passage you see at the center extends from the boiler room deck floor all the way to the top of the ship. This open space is called the fiddly. There's a similar space above the engines. When ships are constructed, boilers and engines are actually lowered down into the heart of the vessel through these wide openings. Getting down to the boilers means traversing multiple flights of metal stairs and gratings. If I bring up Deck C again, you can see access doors in the fiddly, providing direct passage for the firemen and other engineering personnel. The fiddly not only provides crucial ventilation, but also allows sorely needed natural light to filter down into otherwise austere environs below. Our ship has 6 boilers in 2 facing rows. A single boiler stands 15 feet tall and wide, spanning multiple decks. The entire boiler complex is surrounded by huge coal bunkers. Our ship needs to carry around 2,200 tons of fuel to safely make the journey. Sailors, called coal trimmers, continuously cart loads of coal from these bunkers to the firemen working the boilers. Since a ship must maintain its balance, coal has to be carefully removed from bunkers in a planned way. Trimmers might even have to go inside the bunkers to even out coal piles within. Workers in these areas are on duty in a repeating cycle of 4 hours on, 8 hours off. In those 4 hours, a single fireman on our ship will shovel about 2 tons of coal, or around 580 shovels, and that's pretty tame for the standards of the era. Coal soot and dust is prevalent. However, forced ventilation is running at all times, passing huge quantities of fresh air through the space. Let's peer into a boiler to see how this interconnected system works. The boiler is anchored to the ship framing with supports through a raised floor. Firemen shovel coal into a boiler furnace. One boiler has 3 such furnaces that a single fireman oversees. the coal bed is carefully tended to, spreading and throwing coal evenly over the bed for an optimal fire. The fire sits on metal grates. These allow maximum airflow around and through the coals for combustion. While also allowing spent ashes to fall below. They're removable for thorough cleaning. Red-hot combustion gases flow into chambers at the back. And up through many small tubes at the top. Water surrounds all of these superheated chambers and tubes. With some space at the top for steam generation. Thick bolts, called stay bolts, cover the walls of the boiler's shell to safely contain the incredible pressures built within during steam production. Steam flows out of the boiler to the engine room where it's put to work, turning the engine. As the fireman works the boiler, a close eye must be kept on the water level. There's a special high-pressure brass tube with a glass fitting to monitor boiler water levels. Boilers are high-precision instruments designed to operate in specific pressure and temperature ranges. If the water level drops too low, for example, the boiler's metal sheets will easily melt from the sheer heat of the furnace without water to carry that heat away. In the engine room, there's a pump to automatically inject feed water at pressure and maintain proper boiler water levels at all times. Exhaust smoke flows out at the top. Our boilers are equipped with a special system to extract energy from otherwise wasted exhaust heat. An array of small sealed tubes draws exhaust through the air intake chamber. Fresh incoming air passes around these hot tubes and surfaces. Preheating the air before it enters furnaces below through openings near furnace doors. But that's not all. The intake air comes from powerful, steam-driven fans that sit on a grate behind each row of boilers. The fan intake is positioned to generate a strong, continuous current of fresh air throughout the entire boiler room. And also acts as a forced induction system, not unlike a supercharger or turbo on a car engine. In the fiddly, there's the exhaust funnel at the center. With 4 air intake vents at the sides. Down below, next to the fan, there's a crank wheel with a rod. extending to the vent hood all the way at the top. This way, the hood can be rotated from the boiler room to take in the most air from whichever direction. Attached to the top of the boiler, we see various valves. There's the main steam valve that admits steam into the entire ship's steam plumbing. A valve for steam that feeds the extensive auxiliary systems we've seen, like winches and more. And a safety valve to let off excess pressure. An air valve to control the volume of air in the boiler chamber. And a blowdown valve to blast steam out of the boiler at high pressures, which serves to clean internal surfaces between deeper crew cleaning operations while in port. After all that, we still need to get rid of spent coal, or clinker. Furnaces are cleaned out once per watch, scraping the ashes and rubble out, and shoveling it into a tube with a lever that, when opened, admits a high-power blast of pressurized steam to rocket ashes up and out the side of the ship. This rowdy ash clearing system can't be used in port, so instead there's a tube with a hoist for ash bags. That stewards can then empty into a slanted chute for quiet, discreet ash dumping. Boiler exhaust travels up the funnel, which is double-walled since the air gap is a very good insulator to keep excess heat from radiating into the many nearby spaces, and also control vibration and noise. The double-wall construction looks more pleasing to the eye at the visible portion of the smokestack, where the internal tube might quickly become scorched or tarnished if painted. There's a small exhaust at the back to blow off excess steam and keep system pressures within safe levels. Let's bring up the engine room. Here at the top, you can see the rotatable engine room ventilators. And rows of windows, again, to admit as much natural light as possible down into cramped mechanical spaces. As we descend, we see an engine room entry door at Deck C, and a labyrinth of grates, platforms, and steep access stairs throughout the mechanical maze. Both front and back, you can see watertight bulkheads and doors between rooms that, among other things, will help seal against flooding should catastrophe strike. The engines themselves are huge, spanning multiple stories like the boilers. Let's follow the path of boiler steam as it arrives at the engines. There's a main throttle valve here to control all steam admission into the engine. With the throttle open, steam can enter. It flows into a chamber with a moving valve called a piston valve. That holds steam before allowing it to pass into the high-pressure cylinder. The very hot, high-pressure steam is like a tightly compressed spring, so when the valve opens, steam rushes into the cylinder and pushes on the piston, forcing it downward. Meanwhile, the valve has now moved up, revealing an exhaust chamber. Which allows the steam to flow out of the cylinder, having done its work. I'll let it run for a moment so you can see the rhythmic dance between the valve and piston. Steam engine pistons are designed to take force from both above and beneath the piston head. The whole setup is mirrored top to bottom, with another intake and port at the piston underside. It's timed so fresh steam pushes the piston back up after its downward stroke. And the valve opens to exhaust this steam blast as well. You can see the exhaust gets a steady supply of steam from the top and bottom chambers. Which is good because there are 4 total pistons in our steam engine, and they all work pretty much just like the first one. The pistons are sized to match incoming steam energy, with smaller, tighter cylinders for high pressure, graduating to much bigger cylinders when steam energy is nearly spent. In order, steam passes through the high-pressure cylinder first, then 2 intermediate cylinders at the back, and finally, the low-pressure cylinder near the front. They're physically placed out of order, like this, to compensate for different part size and weight between cylinders, for a better balanced engine overall. The size and timing of parts limits how much energy you can absorb at a time. For example, say we only use one huge piston the size of our low-pressure unit. Fresh boiler steam would rapidly explode into the huge space with incredible expansion force, breaking parts. On the other hand, if we use one tiny piston to limit expansion to a manageable amount, now the steam leaves the small cylinder space before we extract all its energy. So these differently sized cylinders and pistons are tuned to get the same pushing force out of vastly different steam pressures. With the steam expansion process happening in 4 cylinders, this is called a quadruple expansion engine. Let's continue examining our engine. The piston rod is supported by a sliding bracket called the crosshead. This is where the piston's up and down power is translated into rotation. With a connecting rod that can pivot to rotate the crankshaft below. Also connected to the crankshaft, we see 2 eccentric rods, meaning off-center. So these rods rotate with their own special timing. Moving up towards the valve, there's an arced bar or link. with a block between them. The block drives the valve. And this is how the piston valve gets its timing. The block can slide along the link bar. If we move the link, the valve timing changes completely. In fact, it's now entirely reversed from what it was just a moment ago. So steam enters the bottom of the cylinder first, instead of the top. Moving the link to the center means very little valve travel, and no steam enters the cylinder. What you're seeing here is not only how we control steam in our cylinder, but also the entire transmission, as it were, for shifting into reverse from going forward. Instead of a gearbox like a car, we change valve timing as the link slides from one side to the other. Of course, these engines are massive, and so are all these heavy moving parts. So there's a steam-powered reversing mechanism attached to the side of our engine. With a long rod that slides all valves at once. It has a lever at the opposite side for the engineer on watch. Commands come in through the engine order telegraph. The engineer can work the throttle wheel to admit more or less steam into the engine. While keeping a close eye on nearby gauges that monitor steam pressure, among other things. To go in reverse, the engineer first closes the throttle, then throws the reversing lever, allowing the reversing engine to complete its motion. Before opening the throttle to match the telegraph command. The huge shaft out the back of the engine is directly connected to the propellers. All this incredible machinery is both the gas pedal and the transmission together. Though it seems like an absolutely wild thing to intentionally run a whole engine backwards from one moment to the next, for a time, during the transition away from steam, These ships were actually known for faster shifting into reverse compared to diesel engines with transmissions. Let's head back to our low-pressure cylinder as steam exits the engine and flows into the condenser to condense from steam back into water. You see, all of the water being used to make steam should ideally be recovered and conserved. You can't use ocean salt water in these sensitive high-pressure systems, so all the fresh water we have at the start of the journey is pretty much all we're going to have for the entire 3,000-mile trip. We need to save every possible drop. There is a saltwater distiller on board to make up inevitable losses, but that's energy inefficient and should be used as little as possible. To cool steam, and therefore turn it back into water, a steam-powered centrifugal pump takes in cold ocean water at the ship's side. Running it through many small tubes in the condenser. Exhaust steam from the engine flows into the chamber. Forming water droplets on the tubes and chamber walls as it cools. While water pools at the bottom. There's an engine-powered air pump to extract air from the condensing process as well. When water turns into steam, it expands something like 1,600 times in volume, condensing or collapsing it back into water and pumping out air creates a powerful suction in the system. This suction pulls steam through the engine, making it more efficient and helping lift the larger low-power piston. From here, water flows through a feed water filter to remove and separate impurities picked up from the engine, like engine lubricating oil. This is another reason steam became so useful, because it can be cleaned and reused over and over. It's called the feed water filter because this water is now destined for re-entry into the boilers. Our boiler feed water continues up high to a contact heater, where exhaust steam from the many onboard machines, like steam winches, mixes directly or contacts the water to heat it up again. For thorough condensation, water is at something like 140 degrees Fahrenheit on leaving the condenser. But it needs to be around 190 degrees for our boilers to avoid inefficient thermal shocks from incoming water. The contact heater is up high, so we can use gravity to ensure all air from contact heating has bubbled out of the water, since air bubbles can cause catastrophic damage in high-pressure systems. Now we have a long pipe full of boiler-ready water at all times, regardless of variances in the running system. The main feed pumps pump water back into the boilers as needed, and the cycle repeats. Also in the engine room, there are other crucial mechanical systems. The evaporator is for distilling or removing salt from seawater. there are backup boiler feed pumps and general service pumps for the ship's extensive water needs. There are engine lubricating oil tanks and pumps. A sanitary pump supplies water for bathrooms, sinks, and so on. An auxiliary condenser condenses steam from winches, the steering engine, and more. A platform up high holds early steam-driven electric generators. Though many onboard systems use steam, electricity was quickly making its way into marine technology. At the other side, there's an entire platform reserved for steam-driven refrigeration equipment and pumps. Behind the engine room, and on decks above, as we've seen, there's a surprising amount of refrigerated space on board. Cooling elements line the walls. Which are insulated with layers of cork panels. And special cement or plaster. Back in the engine room, we return to the main shaft as it leaves the engine. For maintenance and other tasks, the engine can be rotated when not under main steam power, using a small independent steam motor here. With a worm gear that engages with a turning gear attached to the main shaft. The device you see behind that is the thrust block. The engine is designed to impart a rotating force on the main shaft. But the propellers will convert that rotation into horizontal push or pull forces, and we don't want these differing force directions to mix and possibly damage engine parts. So, there are discs connected to the main propeller shaft. They sit in an oil bath for lubrication. These discs press against stationary surfaces in the thrust block, which is bolted to the ship's frame. The block absorbs the force of the entire floating ship as propellers move it through the water. The massive shaft sits upon bearing stools as it makes its way to propellers at the back. With a dedicated tunnel for maintenance access. Our propellers are about 15 feet across, made of a bronze alloy for superior corrosion resistance. Bolt-on blades do affect efficiency, but are easier to replace if damaged or worn. Between propeller shaft tunnels, we see huge freshwater tanks. The hull framing has what's called a double bottom, to make even more space for tanks along the entire bottom of the ship. Some of these tanks can be used to take on extra water weight or ballast water here at the lowest point, to offset consumed coal weight or lack of cargo weight, since the ship should always sit low enough in the water to cover propellers. Ballast tanks can also be used to balance the ship as needed, front to back or side to side. Tanks may be reserved for fresh water, bilge water collection, oil, and more. These ships are much more advanced than I ever could have imagined. Since we often see them in either black and white photos or as wrecked vessels, they appear like ancient artifacts to us. But if we could see them brand new, we would understand how thoroughly modern they are, even though we've learned so much more since then. When horses were still our main means of transportation and work, these highly tuned spaceships were crossing oceans. It truly defies understanding.